Okay, people. Good morning, everybody. It's 10 sharp. So we better start because I know there's a lot of things to learn this morning. So we are having now the last session of Andy Cohen talking about the standard model, or after yesterday's lecture, what the standard model is not. Okay? Andy, whenever you feel.
Okay, let's get going. So a lot to try to squeeze in today. I'll do my best and get as far along as we can. So we've actually laid the basic outlines of field theory. I remind you that really the physics is we have to include relativity with quantum mechanics. That led us to the Fock space. That is, we need to include multi-particle states in the basis states for our Hilbert space. And we discovered that all observables must actually correspond to local operators. And that finally led us inevitably to the canonical quantization of a scalar field theory. And we made the observation, a crucial observation, that we don't have to start with the Fock space every time. We can actually start with the field theory, and we know we're going to end up with the Fock space. So in fact, the field theory in quantum field theory is actually just a convenience to get us to the Fock space that we want with its associated local observables. So we had some discussion by looking at a particular calculation of why the sky is blue to understand how we go about constructing the appropriate Lagrangian, and in particular the interactions that is suitable for addressing any particular physics problem that we're interested in. We discovered this remarkable fact that no matter what choice we made for that Lagrangian, that the interaction among the degrees of freedom that we've included, that if we look at long distances, if we ask a physics question at a length scale which is large compared to any of the intrinsic length scales of that potentially very complicated Lagrangian that we start with, the answer is nearly identical with the one we would get by starting with a vastly simpler Lagrangian. In fact, what we discovered is that aside from very tiny corrections, we need only keep those operators of dimension 4 or less made out of the fields corresponding to the observables of just at the given length scale. And that means that from among the myriad complicated Lagrangians that we might want to consider, we typically only have to look at simpler cases by restricting our attention to dimension 4 or less. And that meant we were all set to actually write down the standard model. We just have to figure out what the appropriate particles are, find their associated fields, and then construct all possible operators of dimension 4 or less, and that will be the standard model. Well, as we discussed last time, that means we have to include all of the fermions. The quarks, the leptons must all be included. We have to include the Higgs scalar, because that's been observed, so we know we need to include that at the relevant scales. And finally, we do have to account for the photon, the W, the Z, and the gluons, which is really the subject that we want to start talking about today. So let's actually start. Sorry, problem with the microphone?
I think you have to lower your mic a bit. It's saturated.
So, I'm sorry.
Yes, there is some saturation in your voice.
I see. Too loud. Let's see what I can do about that. It's the same microphone as yesterday, but I might be able to change that.
No, now it's working.
Okay, so the problem is not the microphone, the problem is me. I'm just extremely loud. So if I get too loud, please tell me to shut up. Okay, so here we go again. We want to understand, oh, back to noisy. Am I still too loud? Let me try the following. How's that? Is that any better?
Yes.
Yeah.
I think so.
Okay, let me try lowering the gain. Give me 1 second. Sorry about this. There we go. Okay, how about now?
Looks fine.
Okay, I'll leave that up just in case. You tell me if it gets to be a problem. Okay, here we go. We want to figure out how to include the appropriate fields for the gauge bosons. And in particular, let's start by talking about electricity and magnetism, the simplest case, and we'll move on to the more complicated case shortly. Well, in particular, what we know about the quanta of the electromagnetic field, the photons, they are massless. And as we talked about last time, the massless representations of the states are characterized by helicity. The photon comes in two helicities, plus and minus 1, corresponding to the well-known two polarizations of light, the left circularly polarized light and right circularly polarized light. So this means that in principle, we should include an appropriate field associated with the creation and annihilation of each of these two helicity states. That is, there should be two fields. Well, we also yesterday talked about the classification of all possible representations under the Lorentz group for the fields, the finite dimensional representations. And we did indeed find some two-dimensional representations. They were 1/2, 0 and 0, 1/2. Those are the only two-dimensional representations of the Lorentz group. However, these are clearly not right to describe the photon. Although they have the right number of fields, they have absolutely the wrong spin. They do not describe particles, even massless ones, of helicity plus or minus 1. Rather, they describe particles of helicity plus or minus 1/2. So these are simply not right. And here we are faced with our first and most significant problem in discussing gauge theory, is that the representation of the states doesn't correspond nicely to the representation of the fields. And this is a big problem. Well, you all know the answer. The right representation for the fields is the 4-vector representation, which we learned yesterday was 1/2, 1/2. That is, the field would correspond to a vector, often referred to as the vector potential. But this has two major problems. The first problem is one of arithmetic so elementary my 9-year-old child could understand it, and that is 4 not equal to 2. We only have two kinds of particles, the helicity plus 1 and the helicity minus 1, yet we have 4 fields, which naively would lead to 4 different kinds of particles, and that's a problem. The second problem is a little trickier, but to notice that for a 4-vector, if we look at the length of a 4-vector, of course, it is the time component squared minus the space component squared. And this means that if we try to include any kind of kinetic term in a Lagrangian, inevitably we're going to have some operators which, acting on states in the Hilbert space, produce negative norm states. That is to say, negative probabilities, which is no good. And that's just because we have a minus sign here and a plus sign here. The minus sign we can arrange to always produce positive norm states, but then unfortunately the A0 will always produce negative norm states. So those two problems are a challenge for us in figuring out how to actually find an appropriate Lorentz invariant quantum field theory that actually produces the proper helicity states for the photon. Of course, these two famous problems have an equally famous solution. We must ensure somehow that when we construct the field theory involving A mu, those four fields, we have to make sure that somehow only two of those fields are really relevant for creating and annihilating particles, and the others play some other role. So in order to understand how this actually comes about, I'm just going to start with the answer. Now, let me be very clear that if I were giving a lecture for a field theory course and we had enough time, I would actually start with the Fock space. I would write down the states which have helicity +1. I would write down the states that have helicity -1. I would introduce the creation and annihilation operators associated with those things. There would be 2 of them, not 4. And then I would do a nightmarish argument involving lots of things, and I would show how the field theory comes about. But because we don't have time, I'm going to write down the answer, which you've all seen, and then understand how it leads to the same conclusion. So the famous solution is to work in the Lagrangian not with the vector potential itself, but the field strength tensor, which is this anti-symmetric combination in indices for the photon. F mu nu is partial mu A nu minus partial nu A mu. And to work with the Lagrangian, which is -1/4 F mu nu F mu nu. So how does this save us? So remember, somehow we want to show that if we canonically quantize this Lagrangian, that in fact, rather than having 4 fields that create and annihilate particles, somehow there's only 2 fields that create and annihilate particles, and the other fields, in some mysterious way, don't participate. Well, it's easy to see, first of all, that F mu nu, and hence the Lagrangian, so in fact, let's say that the Lagrangian does not involve any time derivatives of A0. Just because the only way you can get a time derivative is if you have one of the indices mu and nu being equal to 0, and the only way to involve A0 in the same term is to have both mu and nu 0, but by the anti-symmetry that vanishes. So A0 dot does not enter into the Lagrangian. And that means that, contrary to any naive expectation, A naught is not a dynamical variable. If we write its equation of motion, it will simply be an equation of constraint. That is something that we can eliminate at every time and write down an effective Lagrangian that no longer involves the field A0. Said in a quantum mechanical language, A0 does not create or annihilate propagating states. So that's good. We've already solved one of our 2 problems. By the way, it was A0 that had the wrong sign that would lead to these negative norm states. So we have at the same time solved that problem. But we still have another problem remaining. We only need 2 kinds of particles, hence 2 fields, but now we're down to 3. So somehow there's yet one more field that is not participating. Well, famously, if we look at this particular form of the action constructed out of the square of the field strength tensor, indeed, not all fields participate. There is what's known as a gauge invariance. Notice that if we transform the gauge potential A mu by adding to it a total derivative of some arbitrary function. Whoa, can you still read that? Some arbitrary function lambda of x. If we make this transformation, then F mu nu is not affected. That is, this is a transformation that leaves the action invariant. So for our purposes now, that means that there is some part of the 4-vector A mu which doesn't actually appear in the action. It's a little bit complicated to identify the piece that does not appear in the action. Obviously, it's not any one of the components of a mu. And because there's a derivative involved in the transformation, it isn't any algebraic combination of the a mu's. But nevertheless, there is something, some part of a mu, some functional part of a mu, which doesn't contribute, and that's what reduces the effect of a mu in this theory down from 4 fields to 2. One of the fields is not relevant because there's no time derivative, it's a constraining field, and the last one corresponds to this gauge invariance. It means that there is some differential combination of the components of a mu which is not present in the Lagrangian. Sometimes we refer to this as a scalar part of a mu. How do I know it's a scalar part? Well, because the arbitrariness in the gauge transformation, this gauge invariance, is associated with a single function that transforms like a Lorentz scalar. Okay, now, sometimes people refer to this gauge invariance as a gauge symmetry. That is an inappropriate language. This is, although superficially may seem to have something to do with a symmetry, is totally unlike a symmetry. It arises because we have used a 4 vector with 4 fields to describe a physical system that really only has 2 propagating degrees of freedom, the 2 helicity states of the electromagnetic waves. That's a statement that has nothing to do with quantum mechanics. That's just the classical field theory. When we try to use 4 fields to describe 2 propagating modes, we have an over-complete characterization. In fact, we do this all the time when we do mechanics. When we deal with constrained mechanical systems, we have a cylinder rolling down an inclined plane. Well, in principle, the rotational orientation of the cylinder is 1 degree of freedom, and its location along the surface of the plane is a second, but they are connected by a constraint. But it's quite convenient to keep both of those as independent degrees of freedom in the mechanical system and impose the constraint later. Well, the same is exactly true here. We are keeping all 4 components of the vector potential, even though only 2 of them correspond to unconstrained motion. Which means that because we have used this over-complete characterization of the physical system, and we did it because we wanted to somehow preserve the manifest Lorentz invariance to make it obvious, it means that actually 2 different gauge potentials that differ only by a gauge transformation represent exactly the same physical configuration. They're just 2 different ways of describing the same physics. That is completely unlike asymmetry. So let me give you a simple example. Asymmetry takes 1 physical configuration and transforms it to a different and distinguished physical configuration that nevertheless has similar physics. If we solve the mechanical problem for the first configuration, we immediately know the solution for the second. But it is clearly a distinct configuration. If I were to take myself and perform the symmetry transformation called a rotation, all of you would recognize that I am rotated, for example. So now, let me consider the case of a gauge invariance. I am going to gauge transfer myself. Want to see it again? Okay, hopefully you noticed that nothing happened. A gauge transformation, unlike a symmetry, does not change the physical configuration. It changes the coordinates we use to represent the same configuration. So do not confuse gauge invariances with symmetries. Okay, we still have to quantize this theory, and that leads to yet another problem. we've argued that this particular Lagrangian, the -1/4 f squared, has the right property to only involve 2 propagating degrees of freedom. A0 doesn't propagate, it's a constraint, and then buried here in some complicated way, there is one more degree of freedom, one more field that doesn't actually enter into the Lagrangian. But the difficulty is that if we try to quantize this theory, because we are starting with 4 fields, all the 4 components of A mu, and one of them we haven't included in A4. And when we try to do the quantization, that causes a problem. Well, that's actually extremely easy to deal with. We just have to include an action for that extra component. Notice that because that component has nothing to do with electromagnetism, it doesn't matter what action we include for it. We can include anything at all, because we're never going to ask a question about the physics of that unphysical mode associated with the gauge invariance. Making that choice for what we are going to include in the action, a very arbitrary choice, has a name. It's referred to as gauge fixing. We can think of it alternatively as, well, the values of the A mu's correspond to the coordinates, and there are different choices of coordinates for the same physical situation. Given any A mu corresponding to some physical situation, any gauge transform of A mu is just a different choice of coordinates for the same physical situation. So all we have to do among that large set of different coordinates for the same physical situation is figure out a constraint that picks just one for each possible physical configuration. There are a lot of standard choices for the gauge fixing, and let's just list a few of them. So one, which is probably the first one you encounter when you look at undergraduate electricity and magnetism, is called Coulomb gauge, where we impose the constraint that the divergence of A is equal to 0. This is not a particularly common gauge in dealing with quantum field theory because it breaks Lorentz invariance. Sorry about that. This is easy to find a gauge fixing Lagrangian that imposes this. We just need something that the equation of motion is del dot A equals 0. And I leave it to you to figure out what Lagrangian does that. A second and common choice is Landau gauge. Landau gauge is a Lorentz invariant analog of Coulomb gauge, where we just take the 4 divergence of A equal to 0. This is probably the single most common gauge choice used in quantum field theory. There is a gauge choice which is extremely convenient, and I just want to mention it because you may encounter it. It's great for showing all of the things that I'm saying, which is known as axial gauge, where I simply pick one of the spatial components and set it equal to 0, A3 equals 0. The nice thing about this gauge is, notice A0 is not relevant because it's a constraining field. I've removed A3, so that leaves only 2 fields, A1 and A2, that create the helicity states. So it's an extremely simple gauge to work with because it's very closely connected with what happens directly on the space of states. Okay. There are an infinite number of choices, but one particularly nice gauge is actually a set of gauges sometimes called the arc-C gauges. So what we add to the Lagrangian is minus 1 over 2 times this parameter c times d dot a squared. If you take c to 0, then the equation of motion is going to enforce d dot a equal to 0. That is simply Landau gauge. But we can also make other choices, like c equals 1, which is called Feynman gauge, or c goes to infinity, which is known as unitary gauge. Okay. So all of this is still review. I want to make a connection finally with the last thing we did yesterday, where we talked about spontaneous symmetry breaking. You recall that we argued yesterday that when we have what we called a global symmetry, there was an associated conserved current. And then by thinking about the Ward identity, which said that if we consider matrix elements where we insert a current, with some string of local fields, that this was equal to a sum of the charges under the symmetry of those fields. And we notice that if we take k mu to 0, then the left-hand side naively has to go to 0, which says that the vacuum must be invariant under the symmetry. But we discovered that, of course, it's quite possible that there is a pole in some of the Green's functions, which would correspond to a massless particle, and that would correspond to when the vacuum expectation value of some charged operator is not 0. This situation is called spontaneous symmetry breaking and plays an important role in lots of areas of physics, including in the Standard Model. So an obvious question then is, if we consider our gauge theory, is there any analog of spontaneous symmetry breaking? Well, that's actually the wrong question. There's no symmetry. How could we break it? We just had this conversation that although there is this gauge invariance, it is nothing at all like a symmetry. So how could that possibly correspond to symmetry breaking? Well, the answer turns out to be a little bit subtle. So let's think about our gauge invariance again. We have said that there's an invariance, not a symmetry, under which the vector potential shifts by the total derivative of a scalar function. In order to understand how its relationship with spontaneous symmetry breaking works, we should also include some particles that carry the charge that the electromagnetic vector potential couples to. So imagine I have some, oops, sorry about that. Imagine that I have some charged field phi, which under the same gauge transformation has to change by an e to the I times that field times phi. So this is just a statement that when you make a gauge transformation, when you change those coordinates, all the charged particles also have to change their coordinates by this complex phase. So once again, this is not a symmetry. This is a transformation that takes us from one set of coordinates describing a physical system to a different set of coordinates describing exactly the same physical system. Well, except when lambda is a constant, then this looks exactly like our global symmetry. And indeed, this is a true global symmetry. It is different from the full set of transformations where lambda is an arbitrary function. But when lambda is a constant, it looks just like a conventional global symmetry, and therefore it does what every global symmetry does. In the Wigner-Weil mode, it allows us to classify states according to their charges, which are conserved. And in principle, then, just like we discovered yesterday, it would be possible for some of those charged fields to develop expectation values, and then we would expect to find a Goldstone pole. So this part of the gauge invariance is actually a global symmetry, and then can it be broken? And the answer is yes. But if it is broken, why don't we get a massless particle? Or I should say, do we get a massless particle? It turns out that something interesting happens, and indeed, we do not get a massless particle. That's because although the Ward identity remains true, well, I won't write it again, I just wrote it a minute ago. The Ward identity remains true, and it says there should be a massless particle. Well, that's true. But nobody said that massless particle has to be anything in particular. It just says that we must find a massless particle somewhere in the spectrum. And as we just said a moment ago, when we quantize the photon, we have to include a Lagrangian by gauge fixing for the fields that actually have nothing to do with the propagation of the photon. Those additional fields, which are just constraints, well, they can do whatever they want, and it doesn't have any effect on the physics. So the right question is it possible that the Goldstone boson associated with the breaking of this global symmetry ends up being one of those fictitious degrees of freedom and not the ones that, in fact, correspond to the physical electricity and magnetism? And indeed, although it might be sound a little strange, that is precisely what happens. There is indeed a Goldstone boson, depending on the gauge fixing, which we'll talk about in a minute, but it turns out that Goldstone boson doesn't couple to any physical quantity. So we can have spontaneous symmetry breaking without the presence of that pole. But most importantly, when that happens, it turns out that the photon is no longer massless. Now, the easiest way to explain this is to just do a simple example. So bear with me for a minute. Let's consider exactly the system we just described. Electromagnetism, but we will include a scalar field. Which carries charge. With some potential. And let's assume that the minimum occurs when phi is equal to I believe I called it m in this example. So this is a situation in which the symmetry would apparently be broken. In order to understand the physics of this system, let's parameterize the field phi by writing it's a complex field, so there's some phase, which I'll call e to the I theta of x, and then for the magnitude, I'll call it m plus rho of x. Now, when I plug this back in to see what the Lagrangian looks like, you'll notice that rho of x has some interactions, but rho of x gets a mass. that depends on how high the potential is. So I'm going to take a peculiar limit. I'm going to assume my potential is really, really strong. So the mass of rho goes to infinity. When I do that, it just means that any fluctuation away from rho equals 0 costs a huge amount of energy, and therefore I can ignore it. In that case, the derivative d mu phi, the only thing that's varying is the phase, theta. So this becomes d mu theta plus the gauge potential from the covariant derivative times m. And then when we plug back in, our Lagrangian simplifies. And just to agree with the notation in my notes, I'm going to make this over root 2. So our Lagrangian becomes something very simple. It's just minus 1/4 f squared plus d mu theta plus a squared m squared over 2. And we can work with this very simple Lagrangian to quantize it. Of course, we need to include some gauge fixing, and I'm going to include what looks like a little odd gauge fixing, but it's really very helpful. So there's the gauge fixing term. It's the d dot a, the forward divergence of a, minus m squared, some parameter c theta squared. So why did I choose this particular form for the gauge fixing? Notice that this theory has two different kinds of fields. There's the a mu fields, and there's the theta field. Everything in this Lagrangian is quadratic in those fields. That means it's free field theory, it's completely soluble. Any question I ask, you can answer. The only thing which makes it a little bit tricky is that you may have terms which involve both theta and a. But I've cleverly chosen my gauge fixing so that when you expand this out, there's no term which involves both theta and a. They cancel each other. So this gauge choice that I've just made is a very nice one in which the Lagrangian for the A field is completely independent from the Lagrangian for the theta field. Okay, I'll let you work out the details of that. And unfortunately, I'm going to have to erase what we have in order to go on. With this gauge fixing, when the parameter exceeds to 0, this is Landau gauge. In Landau gauge, you can read off from the Lagrangian that theta is massless. And is the Goldstone boson of the broken symmetry. But in addition to that, if we look at the Lagrangian for A in this same gauge, and I'm not going to write it because we're running a little bit short on time, what you discover is because we've gauge fixed, there are now 3 fields in A which propagate. A0 is a constraint, it's not relevant, but there are 3 remaining fields. 2 of them are the proper polarizations of the photon, and the last one is this gauge degree of freedom that we don't care about. if you work out the propagator, and I encourage you to do it, what you will get I'm writing the general answer. This first term, famously, is the propagator for a massive spin 1 particle with mass m. Indeed, if you diagonalize the matrix on top, you'll see that it has 3 eigenvalues corresponding to the 3 polarization states of a massless spin 1 particle. What about this last term? Well, this last term is precisely the unphysical part associated with gauge transformations. It has a non-trivial propagator because we gauge fix. But in the limit where the Xi parameter goes to 0, we see 2 strange things. First, it becomes massless. And secondly, it doesn't actually couple to anything. However, remember, coupling to the charged particle always comes with the covariant derivative. That is d mu theta plus a mu. And what happens is the d mu theta coupling couples to the Goldstone pole, but then the a mu actually couples to this term, the unphysical mode from the gauge field, which has a negative norm and is also massless, and so cancels in gauge invariant in this combination. Okay, I didn't want to spend too much time on this. This is called the Higgs mechanism, but as a homework exercise, you should just write out the Lagrangian, including this gauge fixing term, figure out the propagators, and understand how the different modes behave. But something truly remarkable happened here. We started with a theory that had a gauge potential with some charged particle, and when we broke the symmetry associated with that charge, it did indeed produce a Goldstone pole, but not one that coupled to any physical quantity, so it was irrelevant. But more interestingly, it ended up with a mass for the gauge field. Sometimes this language, people, physicists say, I say myself, that the Goldstone boson is eaten by the gauge field to become the third polarization, the so-called longitudinal polarization. Well, this little example shows that that's not appropriate language. The Goldstone boson is still here. It didn't somehow magically appear inside the gauge potential. It just doesn't couple to anything. In fact, in other gauges, the Goldstone boson is completely gone. And it's those other gauges, like unitary gauge, which was this parameter Xi goes to infinity, where indeed the Goldstone boson disappears, and now the language that the gauge potential ate the Goldstone boson to give you that third polarization makes more sense. But be aware that language like that isn't universal. It depends on the gauge that you choose. Okay, so I encourage you to work out this example. I just wanted to do it for completeness so that we all understood the Higgs mechanism, and we are now finally ready to work out the details of the standard model. So if I hadn't taken this detour to the discussion of the Higgs mechanism, well, then we'd have a very difficult time understanding how the standard model actually describes the particles in nature that we need to include. But other than that, it's not going to play a particularly significant role in what I want to discuss in the remaining 45 minutes. So it's taken most of these 3 lectures to even reach the point where I introduce the nominal subject, the standard model, but we finally have everything at our fingertips to construct the standard model. So remember the procedure I said we're going to follow. We need to specify the appropriate fields, that is, the appropriate degrees of freedom at the energy scales that we are interested in. We can do that in several stages. We first have to specify the spin, we first have to specify the gauge degrees of freedom, those things that correspond to our helicity plus or minus 1 particles. Okay, that's step 1. Step 2, we have to specify what we usually call the matter degrees of freedom of the Standard Model, which is to say all the non-gauge degrees of freedom. We then have to identify any global symmetries that will constrain the operators that we include. And then finally, we just have to identify all operators of dimension 4 or less. And that's it. And then we will have the Standard Model. So we're going to take each of these in turn. So to identify the gauge degrees of freedom, what we saw in the case of electromagnetism is that the vector potential has to couple to a conserved current. That conserved current is the result of a symmetry, a global symmetry. So in identifying the gauge degrees of freedom, we are trying to identify a set of global symmetries that will become gauged in the Standard Model. Of course, you all know the answer to that. There's SU3 color. Okay, if you don't know the details of SU3, it won't matter very much except to tell you that it has 8 independently conserved charges that satisfy a complicated Lie algebra called SU3. There is an SU2, which is sometimes referred to as weak isospin, or sometimes known as SU2L or SU2 left for peculiar reasons. And finally, there is a U1, which is called a hypercharge. That is the symmetry group corresponding to the gauge potentials that we will include in the Standard Model is SU3 color times SU2 weak isospin times U1 hypercharge. There is then an F mu nu constructed out of a gauge potential for each one of these symmetry charges. So how many are there? I'll put an index A. There are 8 in the SU3. There are 3 in the SU2, and there's 1 in the hypercharge, so there are 12 of them. And the Lagrangian, remember, is going to be all the operators of dimension 4 or less that we can write down that are Lorentz invariant. Well, there's the one that we've already talked about, F mu nu squared. In order to go further, we need to figure out what the dimension of F mu nu is so that we ensure that we're only looking at operators of dimension 4 or less. Well, we've already done that. F mu nu is the same as the electric field or the magnetic field, which we already discovered in our discussion of the scattering of light by nitrogen molecules, is 2. So the operator that we just wrote down is dimension 4. And we're supposed to include it. In fact, with a little bit of thought, you can convince yourself that there are no operators involving f mu nu of dimension less than 4. Well, that's obvious. F mu nu has 2 Lorentz indices on it. I must contract those to make a Lorentz invariant, which means I got to have something else with 2 such indices. So naively, the only thing is f squared. And then this is unique. Actually, there's another possibility, which is using the so-called fully antisymmetric tensor. But this turns out to be a total derivative, and total derivatives don't change the equations of motion, so we don't need to worry about it. So Julian, the index A is just labeling which of those 12 charges I'm talking about. So A could refer to the hypercharge gauge potential, or it could refer to any one of the 3 SU2 weak isospin potentials, or any of the 8 color gauge potentials. So for each of those charges, we introduce a gauge potential and we construct a corresponding f mu nu. Okay, that answer your question? Great. Okay, so for the gauge potentials, the Lagrangian actually has a single unique operator. That's very nice. The only thing is that there can, in principle, be a different coefficient for the different charges. When the charges are connected by symmetry transformations, then those charges must, that coefficient must be the same. So there is actually 3 different coefficients. One for the color group, because all of those 8 potential coefficients must be the same by that symmetry. There's one for the SU2, and there's one for the U1. Those different coefficients correspond to the different strengths, coupling strengths of color, weak isospin, and hypercharge. Okay. That is all I'm going to say about the gauge fields, because the Lagrangian is effectively unique. It is characterized by 3 parameters, the so-called gauge couplings. So far, the standard model is extremely simple. It's a sum of one particular kind of operator and 3 different numbers characterizing that sum, 3 parameters, the gauge couplings. So we'll try to keep count of some of the parameters of the standard model. These 3 are the most important. Okay, step 2 was to identify the fermions, the matter fields. I should have said the matter fields in general. Well, the matter fields we're going to divide into 2 categories. There are the fermions, the spin 1/2 particles, and then there's one scalar particle. So for the fermions, you may recall yesterday I urged you to never use Dirac fermions, to only use Weyl fermions, and indeed that is what I am going to do. So every field I write down will correspond to the 1/2, 0 representation of the Lorentz group, what we called left-handed. Of course, the Hermitian adjoint of these fields will correspond to right-handed representations of the Lorentz group and will appear in the Lagrangian, but I don't need to specify them here. In writing these down, I have to tell you what charge they carry under each of the conserved currents we just talked about. That is SU3 color, SU2 isospin, and hypercharge. So these are the representations of the various fields, and as you'll see, I'm going to introduce 5 fields. The first field I will call Q. It is a color triplet field. that tells you that it comes in 3 separate colors, and those colors mix up under a color transformation. It is a doublet under SU2. That is, it has isospin 1/2. There's a +1/2 component and a -1/2 component, which is why I've written the 2 there to indicate that there are 2 fields hidden in there. If I were to write Q as a 2-component vector, usually we call the upper component U and the lower component D. Finally, I have to assign a hypercharge, which is just a number, and although it may seem peculiar, the hypercharge I assign to Q is 1/6. So let's talk about what particles are created and annihilated by Q. So it's by convention, we first talk about the particles that are annihilated by Q. They are color triplets. Well, fermions that carry color are called quarks. So the field Q annihilates quarks. Which kinds of quarks does it annihilate? Well, there are 2 different kinds corresponding to the different isospin charges. The isospin +1/2 quark is called a U, and the isospin -1/2 quark is called a D. U and D quarks. Finally, both the U and D quarks carry a hypercharge, which is 1/6. So I'm now going to say this all one more time. Remember that these quarks are annihilated by a left-handed representation of the Lorentz group. So if you like, approximately, we can say that Q annihilates left-handed quarks. We'll understand why that's only approximate in a minute. So Q annihilates left-handed up and down quarks that are a doublet under SU2. If I were to look at the Hermitian conjugate Q dagger, what does it do? Well, it also annihilates things, but because it's the right-handed representation of the Lorentz group, it annihilates right-handed things. Because we took the complex conjugate, instead of annihilating quarks, Q dagger will annihilate antiquarks, and they'll have hypercharge -1/6. So the field Q annihilates right-handed quarks, and Q dagger the field Q annihilates left-handed quarks, and the field Q dagger annihilates right-handed antiquarks. Okay, but that's not all the quarks. We should also have, in addition to left-handed quarks and right-handed antiquarks, we should also have left-handed antiquarks and right-handed antiquarks, and we need different fields to annihilate those. So there's another field which I'm going to call UC, or U conjugate. Note that that superscript C is not an operation. It doesn't tell you to do something to a U. It is a completely different field. And probably it would be sensible if physicists called it by a totally different letter to not cause any confusion. As I just said, it annihilates left-handed things. It is a 1/2 zero representation, and I said it should annihilate antiquarks, which I'm going to indicate by a 3 bar rather than a 3. This is a so-called singlet under SU2 isospin. That is, the U conjugate field does not create or annihilate particles that carry any weak isospin. And finally, this carries hypercharge -2/3. There is another left-handed field called a D conjugate, which annihilates antiquarks. They also carry no weak isospin, and carry hypercharge 1/3. Notice that we now have 3 different kinds of quark fields. We have Q, which annihilates quarks, which are iso-doublets. We have U conjugate, which annihilates antiquarks, which are iso-singlets. And we have D conjugate, which annihilates antiquarks, which are also iso-singlets. You may recall yesterday we said that a theory in which the right-handed representations have different interactions than the left-handed representations tells us a theory is chiral. Because I've written this all in terms of left-handed representations, we can see that this is chiral because there's no way to combine these things where the SU2 charges are the same for left and right. For example, let's look at the left-handed quark. Well, there are left-handed quarks which are annihilated by Q, but there are also those are the only left-handed quarks. If I look at U conjugate dagger, it also annihilates quarks, but they're right-handed. So the left-handed quarks are all iso-doublets. The left-handed antiquarks are all iso-singlets, and ditto for the right-handed ones. So this is a chiral theory, and it cannot be adequately written in terms of Dirac spinor notation, although you can stand on your head to try it. This is the complete quark content. In addition, we have leptons, which there's an L field, also left-handed, that we introduce, which will not carry color. It's a singlet under color. It is also an iso-doublet and carries hypercharge -1/2. And then an E conjugate, which is a singlet under color, a singlet under SU2, and carries hypercharge 1. The E conjugate is therefore the simplest of these to understand because it doesn't carry any color and it doesn't carry any iso spin, and simply has a hypercharge of 1. The E conjugate annihilates left-handed anti-electrons. Well, anti-electrons are sometimes called positrons. So E conjugate annihilates a positron. So it also, annihilates a left-handed positron. It also creates a right-handed electron. So where's the left-handed electron? Well, the left-handed electron is annihilated by fields in L. So L, we see here, is an iso-doublet, a weak doublet. So if we write L in terms of its 2 fields, the upper field is I've called nu, and the lower field I've called little e. The lower component annihilates left-handed electrons, and the upper component annihilates left-handed neutrinos. And this little table is the key to the Standard Model. It is a compact and very simple way of saying what all the matter content of the Standard Model is. Once I know these charges, everything is completely determined. Okay, so sadly, I have to erase the table, but hopefully you will remember it. So what is the Lagrangian for the fermions? So we already have our Lagrangian for the gauge potentials. We now need the Lagrangian for the fermions. Well, the Lagrangian for a Weyl fermion involves Pauli matrices and just looks like psi dagger I, the dot product of the 4 Pauli matrices with a partial derivative. But we need to include the gauge interactions. That's easy. The partial derivative should just be a covariant derivative. And here, psi should be thought of as a giant column vector with Q, U conjugate, D conjugate, L, E conjugate. Of course, the way the covariant derivative acts involves multiplying each of the appropriate gauge potentials by the appropriate charge of the fermion. And the covariant derivative, d mu psi, is equal to the ordinary derivative minus I, the gauge potential corresponding to each of the different 12 gauge potentials times a giant matrix TA, where the matrix TA is the thing that incorporates the various charges of all the fermions. So it's pretty compact. Again, we need to ask what the dimension of this giant component of fermions is. It has dimension 3/2. And here is probably the single most important feature of the standard model. That means the Lagrangian operator we've included is dimension 4, and it is unique. There is no other dimension 4 that we can operator that we can write down that is compatible with the gauge invariance and Lorentz invariance. You might have said, well, can't I consider psi dagger psi? Psi dagger psi would be dimension 3. But notice this operator is not Lorentz invariant. That's because psi is 1/2 0. Psi dagger is 0, 1/2. And if I multiply them, I get a 4 vector. But I don't get a scalar, a Lorentz invariant. There is no possibility of combining a psi dagger with a psi and getting something which is Lorentz invariant. Well, what about a psi with itself? Well, this is now 1/2 0 times 1/2 0. Using addition of angular momenta, this includes a scalar plus a left-handed spin 1. So this, in principle, we could make a Lorentz invariant combination to include our Lagrangian. However, if you look at that table that I wrote down a moment ago, we need to write something that is charge neutral, that is to say gauge invariant. And there is no combination of this sort which is gauge neutral. So again, this combination is fully unique. So at this stage, our theory is still characterized by only 3 parameters. The standard model up to now is the gauge interactions of this set of 5 different fields, which includes a whole bunch of different particles, all the quarks, all the leptons, but only 3 parameters. What makes the standard model more complicated and more interesting is the one remaining non-gauged field that we haven't yet included. Even though it's not a fermion, I still have to do the same thing. I have to specify its quantum numbers under SU3, SU2, and U1. This, of course, is the Higgs field, which carries no color, which is a iso doublet, and by my convention carries hypercharge 1/2. Because it's an isodoublet, it's two fields. The upper one is usually called phi plus, and the lower one is called phi 0. We now have to include a Lagrangian for the Higgs field, which is in fact just the Lagrangian we wrote down yesterday. It's the covariant derivative on the Higgs field squared minus a potential for the Higgs. But restricting our attention to operators of dimension 4 or less, there is again a almost unique potential characterized by two parameters, a parameter lambda and a parameter v squared. Of course, this parameter v squared, just as yesterday, could be either positive or it could be negative. If it is negative, v squared is a negative parameter, then the symmetries, the global symmetries corresponding to SU3 cross SU2 cross U1 are realized in the Wigner-Weil mode. All of the gauge bosons create and annihilate massless helicity 1 particles, which looks absolutely nothing like nature. On the other hand, if v squared is positive, then H acquires a vacuum expectation value, just as we discussed yesterday. Those global symmetries are broken, the Higgs mechanism ensues, and some of the gauge bosons acquire a mass. Can we identify which gauge bosons acquire a mass? Well, first of all, because the Higgs does not carry any color, none of the colored gauge bosons acquire a mass. Because it carries SU2 and it carries U1, naively, all of the SU2 bosons and all of the U1 bosons would acquire a mass. However, if you write all of this down and go back to what we wrote yesterday, there is in fact one combination of charges which does not get a vacuum expectation value. That combination is T3. That is, the SU2, there are three generators, T1, T2, and T3. So we pick one of them, we call it T3, and we add to it the hypercharge. That combination we call Q, and it remains unbroken. It's easy to see by convention, as we said yesterday, the vacuum expectation value of the Higgs field, we can always choose to be a real positive quantity in the lower component. T3 on the Higgs is the matrix 1/2, 0, 0, minus 1/2. And the hypercharge on the Higgs, by our convention, is 1/2 plus 1/2. So you see that T3 plus Y is 1, 0, 0, 0, and T3 plus Y, that matrix acting on H, just gives you 0. So that means for SU2 cross, for SU2 cross U1, when the Higgs acquires its vacuum expectation value, of the 4 gauge potentials, one remains massless. This is the one called the photon, and Q is the electric charge. Okay, so the theory now has the 3 parameters, the gauge couplings, plus 2 more. which we called V and lambda. So we're still only at 5 parameters. But interestingly, now that we have included the Higgs, there are further operators we can write down involving the fermions. They are of dimension 4. There are no dimension 3 operators. So there are some new dimension 4 operators. They are of 3 types, and I'm just going to write them down. So they are constructed out of the Higgs and our fermions. The first one is QHU conjugate. First of all, as I just said, the product of 2 left-handed fermions can contain a Lorentz invariant singlet. If I try to write something down with a Q and a U conjugate dagger, that will never have a Lorentz singlet, so you can't have it. The only trick then is to verify that we have satisfied all of the gauge charges. Well, Q is a 3 in color. U conjugate is a 3 bar, and so those can be combined into a color singlet. The quark colors and the anti-quark colors match up to produce a singlet. Q is an iso doublet, as is the Higgs, and you can combine 2 isospin a half into an iso singlet. So these combinations can be made invariant under SU3 cross SU2, and you can check that if you add up the hypercharges, you get 0. So this is a gauge invariant operator. There are 2 more operators that are similar. There's Q, H complex conjugate, and D conjugate. Again, you can check the doublet charges give you a singlet, the SU3 charges give you a singlet, and the reason it's H star is because I had to make hypercharge work. Finally, there's an L H star E conjugate. And that's it. 3 more parameters, the coefficients of these operators. In fact, we know what these 3 parameters are. When the Higgs acquires a vacuum expectation value, if we forget about the fluctuations in the Higgs, then this is a quadratic form in the quarks and the leptons, which correspond to masses. There's the up quark mass, the down quark mass, and the electron mass. And that's it. That's the standard model. Okay, remember, I started these lectures yesterday by saying that the standard model would eventually be relatively simple. We just have to write down all the operators of dimension 4 or less compatible with the appropriate symmetries. And the answer is there are a variety of such operators once we've identified the proper particle content, but not many of them. And this is it. If you add up these 3 things, this is the complete standard model. By the way, these 3 terms are called the Yukawa couplings. If you divide the action for the standard model, sorry, who asked that? I didn't catch the name. I guess I can find out. So the question was, in the tensor product 1/2, 0 with 1/2, 0, there is a singlet, but there's also a triplet. Well, the triplet, the 1, 0, we throw away. We can't include it in the Lagrangian. So if I actually take the product 1/2, 0, remember that's can you see me? That's a 2-component vector. And I multiply it by another 2-component vector. There are 4 things in that product. 3 of them correspond to the 1, 0, and I throw them away. And then there's one particular combination, which is the singlet, which is what I want. And in fact, the singlet is, if you can see my fingers, you take the top component of the first one times the bottom component of the second one, and you subtract the bottom component of the first one with the top component of the second one. Okay, and you can verify just by what you know about spin that that is indeed a singlet. Okay, did that answer your question? Whoever it was, mysterious person. Thank you. Okay. So, there's one caveat to what I just said. I mean, one obvious caveat. The fermions are replicated 3 times. We say there are 3 families. So those Yukawa couplings are actually matrices. They're matrices because, for example, in QH U conjugate, each of the Q's comes in 3s, and each of the U conjugates comes in 3s, and I can couple any one of the U's with the Yukawa coupling to any, sorry, one of the U conjugates to any one of the Q's, so there's a matrix. Well, counting the parameters in these matrices is a bit of a challenge because by field redefinitions of various sort, there's less than there would naively be, but most of the couplings of the standard model, most of the parameters, are Yukawa couplings. Okay. Now, I went through all of this without giving you any hard details about the standard model, but really, in principle, everything is now on the page. The entire standard model we have now justified and constructed, and you can go ahead and start expanding things and seeing what they look like. A good exercise is to start by computing the masses of the W and the Z and showing that the photon remains massless and what the charges and couplings are. Of course, I would do that if we had time, but there's not really enough time. I want to move on to the more interesting things. So I want to point out that we did not impose any global symmetries aside from those that are connected to the gauge invariance. That is SU3 cross SU2 cross U1. We did not impose any global symmetries at all in the construction of the operators. We wrote down the most general Lagrangian we possibly could, incorporating those symmetries. Actually, from our table, you can see that there are some other charges we can assign. We have L, E conjugate, Q, U conjugate, D conjugate. And if I assign a 1 to L, a -1 to E conjugate, a 0 for all the quarks, this is a U1 charge, you can verify that none of the operators we have written down violate this charge. There's another one I can write down. Where I assign a charge 0 to L, 0 to E conjugate, plus a third to Q, and minus 1/3 to U conjugate and D conjugate. And again, you can verify by inspection that none of the operators in the Lagrangian we've written down violate this charge. These two symmetries, which are symmetries of the things we've written down, are called lepton number and baryon number. They are symmetries of the standard model. But notice they are not symmetries we imposed. They are symmetries that appeared automatically. Once we imposed the gauge invariances and the constraint of dimension 4 or less, then we're guaranteed that these charges will be conserved. We call symmetries of this type accidental symmetries, ones that we don't impose, but they arise automatically at long distance. If we were to have included higher dimension operators, like dimension 5, then we can easily write down dimension 5 or dimension 6. We can easily write down operators that do not respect these global symmetries. So accidental symmetries are good. That is, we have an explanation why accidental symmetries might appear in nature. Even if you violate those symmetries at short distances, as you approach longer and longer distances, the effects of that violation will get smaller and smaller. So within the context of the standard model, lepton number conservation and baryon number conservation have good explanations. All we have to do is argue that the physics at short distances is at a very high scale, so that we're looking at length scales that are incredibly large compared to the scales at which lepton number and baryon number are happening. Okay. I have 4 minutes left. Perfect. So I've taken the point of view in these lectures that the standard model is nothing fundamental. Once we know the proper degrees of freedom, that is, the kinds of particles we're describing in a certain energy scale, then we construct the most general Lagrangian involving those things, and we stop at dimension 4 and include only the higher dimension operators when we think we need extra special precision. When we follow this path, which is what we've been taught by Wilson, we arrive at the standard model. Of course, until recently, we did not know that we needed to include the Higgs field. But we've seen it at the LHC. We know the Higgs particle is present. That field must be included in the standard model. Prior to that discovery, the standard model was missing that component. And in fact, theorists had proposed many, many different possibilities for the part of the Lagrangian that broke the electroweak symmetry down to electromagnetism. It was only after the LHC verified the existence of the Higgs particle that we finished that last component of what we now call the standard model. Okay. But from this point of view, of course, the standard model is not fundamental. It is incomplete. There is the physics that will happen when we go to shorter distances. But in addition to being incomplete, the standard model has some major and obvious flaws. And in the remaining 2 minutes, I just want to list the most important of them. The first one, and probably the most obvious, is that there is a force of nature which is not included. There's no gravity here. Now, gravity is characterized by a dimensionful parameter known as m Planck, which is about 10 to the 19th GeV. And consequently, the inclusion of gravity is not essential until we reach a length scale corresponding to a momentum of 10 to the 19th GeV. So it's not really a very serious flaw that at the energy scales appropriate for the standard model, we don't worry about gravity. But as a conceptual issue, it's an enormous one, which has led to so much effort on things like string theory. The next inadequacy is that there are no neutrino masses. Again, when I first started learning about the standard model, there was no convincing observation of neutrino mass. There were lots of hints, but it wasn't obvious. So at that point, it was not clear that the standard model was incomplete, but now we know there are neutrino masses. We have detected them. We have pretty good information about their sizes, and therefore the standard model is inadequate. How do we modify the standard model to incorporate neutrino masses? Well, notice that I told you the standard model that we've written down so far up to dimension 4 is everything possible given the fields that we have. And there are no neutrino masses in that model. So one possibility says that we've missed some fields. We have new degrees of freedom. We need new fields. Well, if there are new fields, we have to ask why we haven't seen them yet. One possibility is that they don't have gauge interactions. If they don't have those interactions, they are very hard to see. This, of course, is a possibility. They are called sterile neutrinos. Note that sterile neutrinos really aren't neutrinos. They're just a new particle, which is not part of the standard model. That therefore has a new field that gets included with no gauge quantum numbers, and so there are new operators you can write down of dimension 4 or less. Another possibility, remember we have repeatedly said that the reason we are restricting attention to dimension 4 or less is just because we're looking at long distances and we know the higher dimension operators make tiny, tiny corrections to that. Well, the effects of neutrino masses are extremely tiny. So it's perfectly plausible that the neutrino masses arise not as operators of dimension 4, but operators of dimension 5. And indeed, it's easy to construct operators of dimension 5 that can produce a neutrino mass. This doesn't require the existence of sterile neutrinos. Certainly, both of these possibilities are of active interest, both theoretically and experimentally, and I'm quite confident many of you are working on this subject. Our third inadequacy is that there's no appropriate candidate to be dark matter. We know about the quarks, the leptons, the Higgs, the gauge particles, and none of them are suitable as candidates for dark matter. That strongly suggests that there must be new fields that we have yet to discover. The observational evidence in favor of dark matter is overwhelming. Sadly, it's not specific enough to give us much guidance about what the new fields that could be dark matter must be. There are lots and lots of possibilities. In addition to dark matter, there is also this mysterious dark energy, which you will hear a great deal more about in the subsequent lectures. The standard model has no mechanism to incorporate dark matter. Dark energy. Indeed, therefore, there must be new components to the standard model that can gravitate in the way that we see in our cosmological observations called dark matter, dark energy, excuse me. Although I've told you that the Lagrangian we have written down is complete and unique, I lied. There is in fact one more operator that we can write down of dimension 4 that we did not include. If we take the field strength for the gluon, and construct the operator F mu nu F alpha beta contracted with the totally antisymmetric tensor, this is usually called F dual. In electromagnetism, this would be a dot product of the electric field and the magnetic field. This is Lorentz invariant, and no reason that we shouldn't include it in our theory. Well, we did mention this briefly earlier, but I discarded it because I said it's a total derivative, and total derivatives don't change the equations of motion. That is true classically. However, as was shown brilliantly by 't Hooft many decades ago, quantum mechanically, there are effects of this operator included in the Lagrangian, even though it's a total derivative. It has a peculiar property, this operator. It violates CP symmetry. It is the in violating CP symmetry, well, we know that CP symmetry is violated in nature, but only at an extremely tiny level. In fact, the coefficient of this operator is often called theta, included in the Lagrangian, and experimentally, theta is less than 10 to the minus 9. But this is quite a mystery, why it should be 10 to the minus 9. The mystery of why it's so small is called the strong CP problem. Okay. I'm going to stop my list of problems with the standard model. I want to write down the names of the others, but they are perfectly good things for you to discuss later with your other lecturers. And I'm not going to discuss them due to lack of time, but I'll write them down here. There is the flavor problem associated with the pattern of the Yukawa couplings. This is an especially interesting subject right now because the LHC seems to be indicating that we might be able to gain some information about this one. The last one, the so-called hierarchy problem, is why does the standard model work so well? And that one is a whole set of lectures in itself, so I think now is a good time to stop. Sorry for the somewhat disjointed way these lectures work. When I'm not in person, I tend to slow down too much. But in any case, I hope that you have learned something about a modern perspective on how the standard model arises, and I hope that we have the opportunity to talk about these issues in person someday. Thanks very much.
Thank you very much for your lecture. I'm reading one question on the chat.
So there was a question that just came up there.
What happens to
yes, sir.
Yes, I got it. So why, for the strong CP problem, we said that there's FF dual for color. And the question is, why is there no FF dual for SU2? And why is there no FF dual for the U1? Well, the answer is different for the two of them. For the U1, 't Hooft showed that, well, in all cases, FF dual is a total derivative. What 't Hooft showed is that when the gauge invariance is non-abelian, the fact that it's a total derivative means that it doesn't affect the equations of motion, but there are important quantum mechanical effects that arise. For the U1, an abelian case, those effects don't happen. So for the U1, the naive argument that it's a total derivative is true, and therefore we don't have to include it. But more interestingly is the situation for FF dual. And this is beyond the scope of these lectures and not something I can explain easily at the moment, but it turns out that the absence of FF dual for SU2 is related to baryon number conservation, baryon and lepton number conservation. It turns out that when you add this operator, it actually is redundant. it can be removed from the Lagrangian by a symmetry transformation. That symmetry transformation is baryon number or lepton number. And that's a very interesting subject, but more than I can explain in the negative 10 minutes that are left. If you want to know, shoot me an email. I'll try to describe it.
Any other question? If not, then thank you again in behalf of all the kids that and thank you very much for these lectures, and eventually for the students we will send you an email how to access the recording. It was a pleasure for us to have you here, and I hope maybe in some other reincarnation of the school you can come in person.
Great. Thank you, Gabrielle. Thank you, all the organizers, and thanks to all the students. I really do hope to meet you sometime in the future.